going to study about the module 4. In module 4, it contains both forced convection and free convection. In module 4, in part A, these are the complete syllabus of part A. In that one, we are going to study about forced convection, boundary layer concept, velocity boundary layer and thermal boundary layer, significance of Prandtl number, governing equations, boundary layer assumptions, integral and analytical solution to the above equations, and some empirical solutions, and the force convection flow over the bodies as well as force convection inside the bodies, means internal flows. These things we are going to be studied in this module. Now come to the basic one, that is what is meant by the convection. Already we discussed the convection in the module 1. Once again the same thing. Here I am going to explain that one. Convection is the mode of heat transfer, one of the mode of heat transfer. In convection, the heat transfer takes place between a moving fluid and a solid surface when there is a difference in temperature. The convection is the mode of heat transfer in which the heat transfer taking place between a moving fluid and a solid surface. Now come to this one. The movement of the fluid is caused by some external agencies, some external agencies, such as it may be a compressors, it may be a fans, it may be a blowers or pump. By using these external agencies to give the movement of the fluid, then it is going to call as the forced convection. Forced convection. Without any external agencies, if the movement of the fluid happens by naturally, that one you're going to call as the free convection. Free convection. Now we clearly understand that what is meant by the forced convection. Here we are using some external agency to give the movement of the fluid over the surface. The next is when the fluid is moved over any surfaces. Now you consider a one plate. Over this the fluid is moving. In this one, the velocity distribution and temperature distribution very near to the surface is very important, very important to find the heat transfer in convection mode of heat transfer. The velocity distribution and temperature distribution very next to the surfaces, very near to the surface, is very essential to find out the heat transfer in the convection. So there is the concept called boundary layer theory, boundary layer theory come into the picture. In boundary layer theory, there are two types of boundary layers. One is velocity boundary layer and another one is the thermal boundary layer. Just I will abbreviate it as VBL and TBL. VBL means velocity boundary layer, TBL means thermal boundary layer. Now we will discuss about what is meant by the VBL. Now just you consider a stationary plate with a fluid is moving with certain velocity. Now I'm going to call as the U infinity. U infinity means free stream velocity. The fluid is moving with some velocity and consider a stationary plate. And this direction I will take as the X, and this direction I will taken as the y direction. When the now you consider, for our understanding purpose, consider the free stream velocity u infinity is equals to 10 meter per second, and this fluid is moving layer by layer, moving layer by layer like that, layer by layer. Now you consider once again for our understanding purpose, consider here there is a 10 layers of fluid is flowing over the surface. 10 layers, 1 2 3 4 like that, etc. Up to a 10 layers of fluid is moving over the surface. When the fluid is moving over here, means over the surface, the first fluid layer, when coming to contact with this surface, try to understand, when this first layer of the fluid is coming to contact with this surface, the relative velocity becomes zero. Relative velocity becomes zero. This one you're going to call as the no slip condition. Means relative velocity is equal to 0 means the velocity is 10 meter per second. We consider there is a 10 layers of fluid is moving, means the velocity of all the layers is 10 meter per second only. When this fluid is coming to contact with the surface, the very first layer, the velocity becomes zero, not 10 meter per second. It becomes, the relative velocity becomes zero, means the plate is stationary, and the first layer means very near to this surface, the velocity becomes 0 meter per second. 0 meter per second. Because of this one, this layer is going to retard the next layer, means reduce the velocity of the next layer. In the same way, the second layer is going to reduce the next layer. Likewise, it will be goes for up to a certain distance, Now I will call this one. At this point, the velocity is 0. Because of this one, that is going to retard the next layer, and that will be going to reduce the velocity of the next layer, and this effect will be up to a certain distance from the surface of the plate. This distance we are going to call as the boundary layer thickness. And above this point, means above this point the velocity is 10 meter per second, but the velocity below this point, the velocity is less than the 10 meter per second. If you find out this point over the entire length of the plate, you will get the profile like that. You will get the profile like that. This delta x means boundary layer thickness varies along the direction of the flow, varies along the surface of the plate. At x is equals to 0, the boundary layer thickness will be 0. But when x is gone changes, the boundary layer thickness is also gone changes. Now this flow field can be separated into two regions. One region is inside this boundary, and another region is above this boundary. Inside this region, inside this boundary, we're going to call as the boundary layer zone or a boundary layer region. Above this boundary, we're going to call as the potential flow region. In the boundary layer region, the velocity gradient come into the picture. Velocity gradients means there is a change in velocity in the below this boundary. Means now we consider, for example, if u infinity is 10 meter per second, below this region the velocity is less than the 10 meter per second. Above this region the velocity is equal to the free stream velocity. In the potential flow, the velocity gradient is not coming to the picture, but in the boundary layer region velocity gradient is coming to the picture. Here we can made into three different zones based on the Reynolds number. Based on the Reynolds number. The Reynolds number tells the characteristics of the flow or behavior of the flow. When the fluid is moving over a plate over the any surface for a particular distance, the fluid particles moves very orderly in nature. Very orderly in nature. That zone we going to call as the laminar zone. Laminar boundary layer zone. After a particular distance, I will call that is the xc. After the particular distance, this orderly orderliness will be going to be changes, is going to be transits. Likewise, somewhat disordered will be takes place. This one is going to call as the transition zone. Transition zone. After this one, the remaining thing is the turbulent boundary layer. Now, the distance, the particular distance after which the laminar flow is jumped to a transient flow. The particular distance where the laminar is going to be changed to a turbulent, that one you're going to call as the critical length. This xc is going to call as the critical length. The Reynolds number at this point, that one is going to call as the critical Reynolds number. The critical length means that is the length where the laminar is going to be jumped to a turbulent zone. Critical Reynolds number means the critical Reynolds number is calculated based upon this critical length. This Reynolds number can be defined as, already we know that Re is equals to inertia force divided by viscous force. After simplification, we will get density, velocity, distance, and viscosity. If this x, this length become xc, this critical Reynolds number become critical Reynolds number. This xc and critical Reynolds is very important while solving the problems. And also this boundary layer thickness delta x also we are going to be found out in the problems. Now we know that the delta x, the boundary layer thickness, is the zone where the velocity is less than the free stream velocity. This is the locus of the points is taken over the entire length. We will obtain the boundary layer. In this one there are three zones. One is the laminar zone, transition zone, and next one is the turbulent boundary layer. Now we are discussing the flow over the any surfaces. Now you consider this is the one surface. There is a or you consider the plate or a flat surface. Over this one the fluid takes place. This type of things will be happen. In this type, the critical Reynolds number can be taken as 5 into 10 to the power of 5. If critical Reynolds number is less than 5 into 10 to the power of 5, then this is the laminar zone. If this Reynolds number, if Reynolds number greater than critical Reynolds number, then that one is going to call as the turbulent flow. If it is less than 5 into 10 to the power of 5, called as the laminar flow. If it is greater than this one, you're going to call as the turbulent flow. This critical Reynolds number is depend upon the smoothness of the surface. If suppose this surface is rough, this value will be changes. If it is very smooth, this value will be changes. If it is any vibration over the surface, the critical Reynolds number will be changes. But we for most of the cases will take critical Reynolds number 5 into 10 to the power of 5. If data is not given, we will consider critical Reynolds number is equal to this much, and this data is also important while we solving the problems. Now the velocity boundary layer we discuss. Next one is the thermal boundary layer. The thermal boundary layer is also the almost the same concept of the velocity boundary layer. Once again, you consider one a stationary plate of temperature Ts, and you consider a fluid is moving with certain velocity and the temperature is T infinity, means free stream temperature of the fluid, temperature of the fluid. Ts is the surface temperature. The same concept, same thing, exactly the same thing, but here we taking as the temperature, here we taken as the velocity. When the here also the same way, we are going to trace the locus of the points where the temperature will be changes. This distance we are going to call as the thermal boundary thickness, delta Tx. For velocity boundary layer, we will take as the delta x. For thermal boundary layer thickness, delta T of x. Below this boundary, the temperature is less, means here below this boundary there is a temperature gradient. Above this boundary, the temperature becomes this fluid temperature. Now this delta of x velocity boundary layer and delta T of x thermal boundary layer is different for different fluids, means these two values is different for the gases, it should be different for the uh, oils, different for the liquid metals. Likewise, this delta x and delta tx is depend upon the Prandtl number PR. This Prandtl number is defined as it is the ratio of molecular diffusivity of momentum to molecular diffusivity of heat. These two values depend upon the Prandtl number. This is the dimensionless number. This PR is defined as molecular diffusivity of momentum to molecular diffusivity of heat. This parameter is related to the velocity boundary layer. This parameter is related to the thermal boundary layer thickness. The numerator parameter is related to the delta x, the denominator is related to the delta T of x. Suppose if delta x approximately equal to delta T of x, then Prandtl number you will get the 1. This is for the gases. In some cases, the delta x value is very high compared to the delta Tx. Suppose in the numerator high value, denominator less value, then you will get Prandtl number is greater than 1. This condition you will see in the oils. Obviously, in the oils, the viscosity is more, means the resistance to the flow is high, so the delta of x is more in the oils. Obviously, in those cases, Prandtl number is greater than 1 for oils. Suppose if delta Tx is higher value compared to the delta of x value, then what will happen? Prandtl number falls below 1. This is for the liquid metals. This condition for the liquid metals. Just now we discussed what is meant by the velocity boundary layer. In that one we discuss what is the laminar boundary layer, what is the turbulent boundary layer, and very important parameter critical length, critical Reynolds number. For most of the cases we'll take 5 into 10 to the power of 5. After we discuss this thermal boundary layer, and finally the Prandtl number, significance of Prandtl number. This all the things will be asked so many times in the examination, means VBL and TBL is asked in the examination, as well as define Prandtl number And what are the significance of potential number is asked in the examination. It is also available in the book and also given in the notes. Please go through that one. Whenever the fluid will be moved over any surface, whenever the fluid will be moved any surface at all the condition, the VBL will be formed. Keep it in mind, once the fluid is moving over the surface, it is nothing but at always the velocity boundary layer will be forms. If this fluid is different temperature and the surface will be the different temperature, then automatically the TBL will also be come to the picture. If different temperature fluid is moving over the surface, means the velocity boundary layer and thermal boundary layer is coming to the picture. In the velocity boundary layer, velocity gradient is there. In thermal boundary layer, temperature gradients will be there. So these things are very essential in calculating the heat transfer, especially in the convection mode of heat transfer. Convection mode of heat transfer. Till now we discuss flow over the surfaces. Flow over, suppose the flow over the surfaces. Now consider flow inside the surfaces. Flow taking place inside the surfaces means inside the ducts. Inside the ducts. Suppose if it is a pipe, the flow taking place inside this one, that one is going to call as the internal flow or flow inside the ducts. Now come to the what will happen, the velocity boundary layer and thermal boundary layer inside the ducts. That those things we will discuss right now. Now you considered this is the one pipe or a circular duct, that is the correct term. Consider a circular duct. This one is the central axis or a center line. Now you consider the fluid will be entering here with some velocity u infinity, that is free stream velocity. When the fluid is coming into contact with the surface, what will happen? When the fluid is coming to the contact with the surface, suddenly what will happen? The velocity boundary layer will be develops. When the fluid is moving along the pipe, means along the z direction, this boundary layer thickness is also grows. This boundary layer thickness is also increases. Finally it will reaches the center of the pipe. In the same way, the boundary layer thickness is developing completely over the surfaces from everywhere, from along the circumference of the surface. This boundary layer finally go and meet the center axis or center of the pipe, or fills the pipe. Fill the pipe. The distance taken by the fluid to up to fill the boundary layer, this distance going to call as the hydrodynamic entry length. Hydrodynamic entry length or our hydrodynamic entry region. This length you are going to call as the hydrodynamic entry length, and this zone you are going to called as hydrodynamic entry zone. Hydrodynamic entry zone. After this entry length, this zone you are going to call as the fully developed flow. Once again I am going to explain. When the fluid enters the pipe, the boundary layer will be starts. As the fluid is moving inside the duct, the boundary layer thickness is also growing. It also go on increases. Finally it reaches to the center of the pipe or axis of the pipe, means along the circumference, completely along the circumference of this pipe. This length you're going to call as the hydrodynamic entry length, and the zone you're going to call as the hydrodynamic entry zone. Behind this, after this point, you're going to call as the fully developed flow. Once the boundary layer fills completely inside the duct. Suppose if you draw the velocity profile here, you will get this type of shape. This velocity profile is Same in after this point. In fully developed flow, this velocity profile will be the same. It is not going to be changes. The same velocity profile will be obtained in the fully developed flow, but the velocity profile will be varies in this zone. This is for the velocity boundary layer flow inside a ducts. Flow inside a ducts. Now come to the TBL, thermal boundary layer flow inside a ducts. The same profile will be obtained, the same phenomenon will be there. Instead of telling U infinity, you are going to tell as the T infinity. Here also the same profile will be gets, but this zone you are going to call as the thermal entry zone or thermal entry length. Instead of, if you consider TBL, this becomes a thermal entry length. The sketch will be the same thing. Here also, after the filling the thermal boundary layer, the next the zone you're going to call as the thermally developed flow. Means after this zone, once again the temperature profile will be the same thing, but before this zone the temperature profile is not the same. Exactly almost the same thing, but very careful when you are talking about the TBL, you should be talking about T infinity. When you talk about the VBL, you should tell about U infinity. Now we discuss the VBL and TBL for flow over plates and flow inside a ducts. Flow inside a ducts. In the examination also, you should aware that for which condition they ask, whether for the plate or whether for the ducts. Based on that one, write in the examinations. In the flow inside a duct, here also the Reynolds number will becomes, if the Reynolds number is the Reynolds number, now it is going to be defined as density, velocity, diameter divided by viscosity. This is the diameter for a flow inside a duct. For a flow over a plate, what we taken as the length. Flow over the surface, we take this is the length. For a flow inside a duct, you taken as the diameter. Here if it is critical Reynolds number is, in most of the cases we take 2300. If Reynolds number is less than 2300, then we're going to call as the laminar flow. If it is greater than 2300, we're going to call as the turbulent flow in a duct. Always keep it in mind that there are two conditions for a flat plate or a flow over the surfaces. For a flat plate over the surfaces, the critical Reynolds number we taken as the 5 into 10 to the power of 5. If it is less than this one, laminar. If it is greater than this one, is the turbulent. But in the flow inside a duct, if the Reynolds number is less than 2300, it is the laminar flow. It is greater than 2300, that one is the turbulent flow. It is very important while we solving the problems. Now come to the syllabus. What are the things we discuss? Just now we studied what is meant to the force convection. Already we studied in the module 1. Now we discuss the boundary layer theory. The VBL and the TBL we discuss, and what is the significance of potential number, and we define the potential number. If it is less than 1, greater than 1, equal to 1, for which fluid we have to be taken, those things we discuss. And the next is the governing equations. That is, governing equation means continuity equation, Navier-Stokes equation, energy equation. These things you already studied in the fluid mechanics, and also I given the notes. Please all student go through that notes. If you not understand, once again I will make the video and I will send that one. And these are also the derivations, the boundary layer assumption. For these derivations also I sent the scan copy of my notes. The next is the turbulent flow. Once again, the turbulent flow is already we discussed just right now. If it in a duct, if it is greater than 2300, that is the turbulent flow inside a duct. If it is a flow over the plate, if Reynolds number is greater than 5 into 10 to the power 5, we consider as the turbulent flow. In the next video, we are discussing about this various empirical solution. In the first this video lecturing, we understand that there are two conditions. One is flow over the surfaces and another is the flow inside the duct. In each condition, there are different zones, that is laminar and turbulent. Here also in the flow inside the ducts, here also you'll get the laminar flow and turbulent flow. There is a different conditions will be there. Those things are right here. Forced convection, external flow, internal flow. Okay, here flow over the flat surface, flow over the cylinders, over, and flow over the spheres. Different conditions will becomes, whether it is the laminar flow, in each cases laminar flow, turbulent flow, laminar flow, turbulent flow, laminar flow, turbulent flow. For the internal flow means flow inside a ducts, flow inside a pipe. Here also the cross section will be changes. It may be circular duct or a square duct or a rectangular duct or a oval duct. For all the cases, the equation will be the different. That is what here telling various empirical solution. These things will be shown in the data handbook, that is heat transfer data handbook. For all these different condition, the equation is available in the heat transfer data handbook. We will solve some of the problems using the different conditions by using the data handbook. Those things I will be explaining in the next video. Thank you.